your right side, the contour line, basically the transition was at the ramp, at the bridge. So there was a comment, that it was going to be very difficult to build this surface at this bridge. So then we decided on your left side just to move the transition out of the bridge. So the transition will start at the MSC ramp on the left. So that will make the construction of this ramp easy. So here you can see the layout of the framing. You can see all the girders that are taking the flares. There are this girder that I am pointing with my mouse. The girder A has a post tensioning that is inside the cell of the box. Similar situation, girder 13, there is a post tension block inside the cell. So later on, we have some problems pre-stressing this girder and this girder. All the post tensioning was said to be stressed from the bend 2, which is where I am pointing with the mouse. For the live load, well, I can mention that this was not a very common bridge. I was not able to use the spine model to do the bridge because the irregularities that has in geometry. So I had to use the Grillage method, and the software that was available for me at that time was MIDAS. It was in 2015. So there are some conditions about the live load, how to apply the live load in the Grillage method. I will talk about that later. Next, this was one of the first projects that we used columns in front of the MSC. Typically in NDOT, we put this column behind the MSC so you don't see them. But for this particular case, we wanted to make this an independent from the MSC structure. There were some difficulties here where you can see the sections on the circle on both left and right, where you intersect the existing bridge. The material that we used to join the bridge to the existing one is just a compression seal material. So this bridge moved independently from the existing one. Here you can see some details where there were some problems because the high skew at the joint. We have to revise the details in order to fix these problems. Here we can see the recess detail. The recess detail, this is at the bend 1, where you can see the approach slab and the bridge. There were some issues also because congestion of reinforcing. You can see here on the pictures, this is the recess where the armor joint is going to be in place. So there was a very difficult to install those things because of congestion of reinforcing. Here we had issues the stressing on this. As I said, all the stressing was on the bend 2, and there were issues stressing because the rebar, the closure pore. There was a closure pore between the new bridge ramp and the existing one. So this closure pore area had a lot of reinforcing that was very difficult for the contractor to stress all these girders. So then we change directions and say stressing from the other side, except for the girder 8 and 13 that it was not possible for the contractor to stress it from the inside the cells. So then after these bars were cutted, and only at this location, girder 8 and girder 13, we use these couplers to restore the length of the bar. So here is the change that we made on the plans to stressing from bend 1. We need to make some adjustment in the reinforcing at bend 1 in order to stress from this side. As you can see, we have to clear all the reinforcing in order to pre-stress from this side. Here are some more pictures showing the details of the blockouts. When we stresses the girder 8 and 13, yeah, there were definitely some issues installing these big jacks. Sometimes we had to allow the contractor to cut the strands in order to let the jack out. It was kind of after they stressing the strand was now in conflict with existing bridge. They were not able to remove the jack after stressing, so I allowed them to cut the strands at the end of the jack. There were some details that we had to modify during construction, like these ties that goes around the ducts, the post-tensioning ducts. They were not, the contractor was not able to install these at the bottom tendon, so we have to make some field adjustments. So I guess they will need more coordination between the contractor of the reinforcing and the contractor of the post-tensioning to make this happen. So we revised the shop drawing, making sure that there were no conflicts between post-tensioning, because there were post-tensioning of the girders and there were post-tensioning of the bend. So those conflicts, we have to clear them during the review of the shop drawings. To hear the details, you can see post-tensioning coming from the girders and post-tensioning coming from the bend. Here are more pictures about the tendon layout during construction. This is another situation where we had to modify the column reinforcing in order to let the tendon go without conflict of the column reinforcing. For the middle column at the bend 2, we had to change the reinforcing to hook. Not all of them, just only the ones that are were in conflict with one of the tendons. So you can see here in the picture, the tendon is crossing the column, so we hook those reinforcing to get the developing length. Here you can see another picture for they install the tendon. Here this space for the tendon to go through. After the construction, we found some concrete consolidation problems in between the bottom slab and the bend cap. And I think the explanation of that is because they pour in red. This is the first pour that they have during construction. And apparently this joint was not ready for that. So here you can see some pictures during the pouring of the bottom slab. Another thing here is the detailing of the top slab reinforcing. I had to bend this reinforcing in order not to be in conflict with the longitudinal reinforcing from the deck. And also it had to be short enough so don't overlap the reinforcing that is in the transverse direction. So we had to make some field adjustment in order to avoid that problem. Here you can see the pour sequence. The red zone is where they were able to use this A-frame deck. The bid well was not able to be used in this type of project. For the other zones, green and yellow, they just use a regular pour. Here are more pictures about how they were doing using the wet burlap for the concrete curing. That is typical in dot construction. Another more pictures how the finish is. So this finish on the picture on the left is because the sidewalk, there is going to be a sidewalk on top of that. They were not too much concerned about how the finish of this area was compared to the other one where it's going to be the road surface. During the air test, there were some issues that it was not possible to have the pressure according to our specifications. We stress at the beginning and also after install the tendons, after we stress the tendons. So there were some safety issues too. There were people cutting, workers cutting inside the cell, and fortunately they were using this power gas, and they had to be taken to the hospital for poisoning. During the air test, after the stressing, the same girders had a problem. They didn't reach there was a leak somehow. The contractor took the risk because they said that they didn't have a safe access to access those girders to address the air leaks. So they decided to grout at a slower pace to help seal any leaks. So after all, the grouting procedure was successful, and we didn't have to worry about this. I can show some pictures on how they were releasing the false work using this, breaking these sand jacks. And after that, I can tell here how the false work dropped immediately. We were surveying or controlling the elevation of the camber at different times in construction, comparing what is measured according to the plans. They were very close. We specify. Here are more comparison about the camber diagrams during construction at different times. There was a change order in this project of $19,000, and that is because it was not predictable to see how was the existing rough surface of the existing bridge. So we have to make some work in order to match the new structure. Here it was decided to do that groove perpendicular to the alignments, but it was in a skew to the expansion joints. There was some issues of bulging the MSC wall panels, but we are still monitoring this bulging. Related to the traffic, here is a view of the striping for contract plans, but we had to make some improvements to this striping because there were some issues related to people driving in the wrong directions. So there were some modifications. Everything that you see in red, there were traffic improvements to make sure that the people don't go and take the wrong way directions. Here is the final traffic striping pictures. We have my information. If you have questions, you can email me and call me. I'm going to proceed with the next presentation that is more related to the MIDAS use. For the MIDAS, I have to say that this was a very challenging geometrical project, so I had to decide to use the Grillage model in MIDAS. So in the office, even though we use Microstation, so that's how I start drafting this layout, locating all the joints and cross elements to make the grillage. There are intermediate diaphragms which are showing here in the mouse, but not too many, like the 1, 2, and 3 only. The rest of these lines represent the slab, top and bottom. Here is how, after laying out all the elements in Microstation, I was able to export those in a DXF extension, so I can be later imported by MIDAS. So here is when I open MIDAS, and then there is an option to import the DXF file. You can see that here. I'm looking for the file. That in this case, the DXF file is centerline plus shape. Here is after the file is imported, you can see the model. I'm going to talk a little bit about the live load distribution because MIDAS has two options. One is the define the lane elements. That this is very typical in a spine model. We use that in a regular bridge. We define the spine model. We define the lane elements, which is basically the spine elements, and then we define the eccentricity of body. For this grillage method doesn't apply to us, so we had to use the cross beam, where you can see the girders are defined, main girder 1, main girder 2, main girder 3, and we define also the cross beam elements, which is in certain cases are the intermediate diaphragms, and in other cases represent the top and bottom slab that connect the girders. So this is very interesting. We have the wheel load, and the wheel load is distribute the load to these cross beam elements, which take the loads to the main girders. In case that we have very large curved bridges, we have to make sure that the spacing of these cross elements are very dense enough in order to make it work. Here is a view where I select or I highlight in red all the cross beam elements that are going to be used to distribute a live load to the main girders. So now I'm going to talk a little bit about the definition of the live load analysis. In Microstation, I make some sketches defining the lane loads, the lanes, the traffic lanes, trying to find the maximum forces that can be acting to the girder. For example, in girder 1, which is this one, exterior one, the most left exterior one, I push all the lanes to the left with all the tracks also as much as close to the left. So this is like basically at the face of the barrel rail, 1 foot 6 inches. Start the track, and then the wheel spacing is 6 feet. So I continue for the next girder 2, and also I move the tracks and the lanes according to create a maximum stress to the girder 2. And I continue the same way for different girders. No, girder 1, 2, this is 3. So I put the wheel load just on top of girder 3. And I accommodate the other tracks accordingly. So I continue with that process for every single girder. So I need this information in order to put that to MIDAS, because MIDAS need the eccentricity of the track at every location. So I'm going to continue with girder 7. Here in MIDAS, then I start input the information. As you can see, I start with girder 1. I define the wheel spacing 72 inches, and then I define the elements that are part of the girder 1, which is basically all the elements that are along this line are defined here in these columns, and the eccentricity of the lane. So, which is the distance between the lane and the elements. The eccentricity is 18 inches in this case. I define the location of the span, which is the first element here, this end. And these two dots that you can see here on each side represent the wheel loads, 72 inches spacing between these two constantly. Then I continue the same thing for the lane 2, acting on girder 1. Define the eccentricity. In this case is 162 inches. That is the distance between the lane, the traffic line, to the element. This, right? Then I continue with lane 3, right? Lane 3, always the reference is this girder 1 element. Now I continue with girder 2, so my reference line will be the girder 2 element. Then I put for the lane 1, I include the eccentricity for the first lane, and then the eccentricity for the second lane. In this case, is this distance from lane 2. The element is 180 inches. And finally, girder 3. And so on, I continue and I start defining all the traffic line lanes. You can see on the left, all the traffic line lanes I define 7, 8, 9, 10, 11, up to 21 traffic line lanes. You have to study all these cases. I will just go and browse quickly because time. And the last girder traffic lane 1, lane 2, and lane 3. Then I will continue defining the track. In Nevada, we use the HL93 and the P13, which is the California vehicle. So once these are defined, then the next thing is defining the moving load cases. In this case, I have the lane. I use the traffic line lanes, which is here. I am circling with the mouse. And I'll also define the vehicle that is going to travel in these 3 lanes. And there are different scale factors according to the multiple lane factor. If one truck is running in 1 lane, the scale factor is 1.2. If there are 2 lanes, 1. This is for code. When there are 3 trucks running simultaneously, the scale factor is 0.85. So then I continue the same thing for, in this case, for the P13 track. And so on. I continue now for girder 7. I define the 3 lanes. For the HL93 traveling, so the specific multiple presence factor here. Again, for the P13, for the girder 7, for the girder 2, HL93, and P13. So for each girder, I have to define 2 tracks, one for the HL93 and another for the P13. I continue so on for other girders. Girder 9, girder 10. So sorry, this is girder 4, P13, girder 5, Together 6. Okay, so after this, I'm going to talk a little bit about the Astro LRMD. I use this MIDAS to design the bridge. The low combinations factories from Astro, that's the one that I use. Here I have the specifications or the first. I define this as a PSC elements. So everything here is for the design of these post-tensioning elements. So I have to define the code. I have to define the reinforcing at each section, reinforcing at the top, reinforcing on the bottom. Also, I have to put the information of the shear reinforcing that I'm going to use. And I have to define all the load combinations for the concrete design according to the Astro. Well, I specify more details for that. All the HL93 combination, I have to combine all the loads and get the maximum and minimum in each case. Here is for the P13. Then service, which basically dead load, additional dead load, HL93, which is the envelope of all the lanes of the moving loads. And also the tendon, forces. So these are the scale factor for service. Then for service 3, strength 1, same thing, but now I'm including the load factors according to Astro. Strength 2, the load factor. Here I'm running just as an example for the bend number 2. The capacity is all this envelope, that vertical dash, right? And the demand is this solid envelope, right? The positive moment, the negative moments, all, as you can see, all the reinforcing works for this specific design. Here, the software has the capabilities to check the stresses. As you can see, all the stresses here are in kips or square inches. All the checks work for this particular. As an example, I'm showing the results for the girder 5. For another example, I'm using the girder 3 now for checking flexure. The software has the capability to verify the capacity and demand. So this is these are the comparison of the capacity versus the demand. All the factors are more than 1. So this is another example of how, for the girder 2, how the check is also the shear is checked. And now I'm going to talk a little bit about Astro LRMD, the low rating. In this case, we use the manual for the Astro manual for bridge evaluation. It has its own load factors that are different than the Astro design. And that's basically the reason how, I mean, the idea is that MIDAS will calculate the rating factor based on this equation, is capacity minus dead load factor from this table times the moment or shear, that element minus the additional dead load factor times the dead load, moment, or shear, whatever we are evaluating, or we are evaluating a rating factor for shear or for flexure, and also account for the post-tensioning. And that is divided by the live load, so that we are going to find out how much live load we have over the actual one that is specified. So if the rating is more than 1, everything looks good, no problems. If not, then there are other things that we have to be done, like well, in supposing a new bridge, this has to be 1, but when it's an existing structure and the loads are different now, there are some retrofits that can be done, or maybe posting the load in the bridge, depending on how much is this value less than 1. So here I evaluate well, so I use the rating option here in MIDAS. You can see here for the design I use PSC, but for the rating I use this other option here. For my particular case in this project, I use the PSC bridge. I had to define the bridge load rating parameters. You specify the allowable stresses for compression and tension in this. Then you define the groups that you are going to rate. In this case, I create groups for girder 1, girder 2, girder 3, and which basically are all the elements that are aligned along the girder wall. So then we specify the, well, we can modify the concrete specifications. If this is an existing bridge, we can modify this, giving more capacity, because old bridge play with that. But in this case, I didn't modify it. This is a new bridge, so these values are basically the same one that I used during the design. Here, I select the load combination that I'm going to use. I have to define for girder 1 the load factor that is applied for HL93 according to the Astro LRMD. I have to use a live load factor of 1.35. As I said before, that factor is the factor that we use here. This value is the one that we are specifying right now. The value again comes from 1.35, which is the one that we use for the HL93 vehicle. But again here, then as an example, I'm showing here the rating values for a specific element. So this is the girder 1, girder 2, girder 3, girder 4, girder 5, up to girder 7. All these values were rated, and we have here the HL93 and P13. All the values are more than 1. That was our goal. Hence, we designed this for the code. And here is the example of the output for the shear. So the MIDAS can give you separate results for flexure rating and also values for shear rating. In this case, what is controlling the design is the shear. It's very close to 1 at this location of the girder 1 and girder 2. These are the lower values. These are controlling the rating. Okay, so I think this is the end of the presentation. So we have time for questions. Thank you.
Okay. Thank you, Percy. So what we're going to do right now is take a few moments to kind of get some questions in and deliver them to Percy so he could answer them for the group today. So we'll take a couple more seconds to kind of get people to send in their questions because they're coming in actively right now. So I'm gonna take control back of the presenter mode, and I'm gonna deliver the questions on screen for everyone to see. Okay.
Okay.
Okay. Okay, Percy, if you could direct your attention to the screen. These are some of the questions right now that I was able to put up onto the PowerPoint. So if you could just go over those one by one and just kind of detail out I guess, your solution or your input or your opinion on those, that would be very helpful. Thanks.
So the first question is, when calculating section capacity using MIDAS civil program, how did you account for main reinforcement in the section? So the software has the capabilities to lay the reinforcing for flexure and shear. So I had to go through iterations. First, start with some assumptions about reinforcing until it works. So maybe there is another way to do it, but that's how I did it. So I input the reinforcing. If that didn't work, I had to increase it until I feel comfortable with the design. The second was how was the PTPS force effects from the skew curve girders to the straight girder was considered. Yeah, I modeled the post tensioning in MIDAS too. So I don't see if I can show that right now, but yeah, there is an option in MIDAS that you can model the post tensioning and take all the effects, the analysis. And the other part is pre-stressing force and input in the analysis phase or in the design phase, or pre-stressing force and input. Yes, so I use the pre-stressing force as an input, not the program didn't design the pre-stressing force. So it's kind of an iteration thing. So I try a pre-stressing force and see how it works, and then I increase or decrease accordingly. So in the other is the equation for forces uses a power of 2.5 and a denominator of 2.37H. This is not the same as what is cited in the research paper. How did you get to this equation? The research paper recommends using a power value of 1, 2, and Caltran using 2.5. Equation for force uses a power of, I'm not sure where is this. Maybe I can talk about that. Whoever sent me this question, maybe you can email me that, because I cannot understand about this power of 2.5. Can you explain a little about boundary condition support use? The columns, initially we were playing with different conditions, boundary conditions. At the beginning, we were connecting this ramp to the existing one. and we evaluate the results, and we were affecting the other existing bridge, so we decided to separate them with a expansion material. Now both bridges work independently, and then also we play with different conditions connecting the columns to the superstructure. So I was playing using hinges, but there were some comments from the independent checker about how those hinges would work, if those are effective or not. So at the end, I decided just to have a rigid connection between the columns and the bridge. So everything is reflected in the analysis. Can I go to the next more sets of questions? I only see 4 right now.
Yes, there were some people asking questions, but it seems like due to the time they have left, as well as they're not complete questions, so I kind of refrain from putting them up on the screen. We'll take another couple seconds to see if anyone else has any questions. If
Okay.
not, we might be able to close off the session here.
All right.
There is, so a few people have completed more questions. Give me a second. Okay. In this case, instead of putting it up, I'll just read it out to you. Okay, Percy?
Okay.
One of the questions asked, is the use of strength of concrete and steel too optimistic?
Steel and concrete optimistic. I don't think I can follow the question. What is the intention of the question?
Okay, to clarify then, for the person who asked that question, I believe it's Stanley Shum, if you can clarify a little bit more into the chat box, we'll make sure that Percy gets to that question. In the meantime, the next question I'll move on to is, did the high skew put additional force in the bend cap? Was the bend cap post-tensioned?
Yes, the bend cap was post-tension. The small bend cap at the beginning, it was just a regular concrete post-tension, no post-tensioning cap. That's the one that is connected next to the ramp, the MSC wall ramp. But the other, the larger one that is in skew and is next to the existing bridge, that is a post-tensioning bend cap. Yes, and since the grillage was modeled, all the skew effects were considering in the analysis. Yes.
Okay, that kind of answers it. So I got the second portion to the question that was asked by Stanley. He says, in any reserve on the strength of the concrete and steel was what he was referencing to.
Any what?
Any reserve.
Any reserve. Well, I use during construction, it was found that after the test of the cylinders, the concrete had more strength than we specified. That's one thing. About the steel, when we the seismic analysis of this bridge was not basically following. It was based on the force design method. So we follow the Astro requirements to increase the capacity of the strength of the concrete and the steel. There are more guidelines if we use the design spec from Astro that requires specifications about the concrete and steel. But that is more for the displacement-based method. In this case, it's in Las Vegas. The seismicity in Las Vegas is small. So I decided just to use the force-based method, make it simple. I don't think that we had to increase concrete strength or steel. So any resistance strength. Yeah, I will say if we follow the displacement-based method, there is definitely more capacity in the concrete and steel. Yes, there is. And then the highest Q put additional force in bend cap. Was bend cap post tensioning? Yes, I answered that question, right? I mean, yes, the bend cap next to the existing bridge is a post tensioning, and the skew is already modeled in the Grillage method. It accounts, which is different in a spine model. In the spine model, the skew is very difficult to evaluate. You know, sometimes we have to create, apply some additional factors that are depending on the skew angle. In this case, you model the whole bridge. That is not, I mean, that is already accounted in the analysis.
Okay. There is one more question. I'll address it here. And I think this might be our final question of the day. And then we'll thank Percy for his time and his presentation for the project. If you look at the third question, Percy.
Using Grillage model, did you account for the self-weight of beams? So how did you manage when transverse beams cross longitudinal beams at the joint location? Okay, so those elements that represent the slab that are perpendicular to the beams, those don't have weight. The weight is zero because all the weight is considering in the beams. So basically, those transverse elements only work as only show stiffness for bending but not carry any weight. So it's just like I would say like a fictitious elements, but definitely they are representing the stiffness of the slab. That is at the joint location. Yeah, so I would like to show a picture of that, how this option in MIDAS work. So you can define all these elements. The beams can be modeled as eye girders, so which is already accounting for the slab. So all the weight and properties of the beams account for the slab in the longitudinal direction, but the connection between these elements are the slab in the other direction is also not adding weight, but influence the stiffness. So I have to define area, inertias of those elements. I think that answered the question.
Okay, thank you. Percy, thank you so much for taking this time and answering those questions. And I think everyone else appreciates your time and the presentation you have given today. And to the rest of everyone, all the attendees and the registrants, we would like to thank you for sitting in on today's session. If there are any other questions, and Percy did put up his email address and his contact information. So Percy, is it okay to share this contact information with those who ask for it?
Yeah, sure.
Okay. So we will share his contact information for those who have requested it. But just to kind of give you a recap, if once the session is over, we have recorded the session and it will be being posted up on the review page, and we will send an email with the Q&A part of it as well. So without further ado, we would like to thank you again for your time. Percy is actually one of our expert influencers, just a network that we have set up to invite engineers to kind of come in and share their, well, everything actually. Just have a chance to discuss a little bit more about what they're going through. It's a community where we have open forums and have engineers able to cross-share and discuss across the platform and across the country. So if you guys are interested in this, Percy is one of the expert influencers on this as well. And you would have an opportunity to speak with other expert influencers similar to him when you join the network. And it's all for free. Other than that, that's it. We would like to thank you again for your time for this afternoon, and have a great day. Thank you, and thank you very much, Percy.
You're welcome.